Hello, my name is Andrew Jessup.
My name is Rashid Ayub.
My name is Liam Wynn.
My name is Andrea Bukuru.
And we are Team Pac-Man. We also have our industry mentor, Dr. Islam, and our faculty mentor, Dr. Kitchen. Increased interest in high-speed data applications for space and military has sparked an interest in the technology we're building. Many of these applications require high power at high frequency, which can be difficult to maintain. We are building a part of a transceiver, which will ultimately be the product that we will be selling to customers such as NASA, Skyworks, and Fujitsu, with future applications in terahertz technology.
So the focus of this project will be only on the power combiner. The unit power amplifier will be provided by Cactus Material, and we as a team hoping to use the least amount of power amplifier to get an output power of 2 watts. So we weren't sure about what combiner to use previously. So the team has decided eventually to use a GISO combiner. So we were working on the layout and optimizing the GISO combiner schematic. So the next step is place an order to Cactus Material so we can get a prototype to fabricate the product.
Okay, so for the schematic of our GISO, we can see that we have 2 input terminals that are in parallel with our output, which is beneficial to us because once we do the combining, we'll have less space taken up, which is one of the specifications of our design. Also, the resistors are grounded, so the electrical length doesn't necessarily need to be 0, and so the parasitic resistance is much smaller than that of our previous design, which was the Wilkinson. And previously in the Wilkinson design, we had a resistor which was in the center, which is also hard to implement in the layout. And the GISO also has a much better thermal management scheme to it, which will be beneficial to us next semester when we do the thermal management strategy. Here we can see our simulations. So the input reflection coefficient, output reflection coefficients, and isolation should ideally be 0, but we know that in real life we can't achieve those numbers. So next we can see our transmission coefficient, which is ideally our most important number, and we can see our insertion loss is about 0.979 because ideally it should be a 3 decibel transmission coefficient, and then from there we can see the loss magnitude, and this number is important because if we have a 4 watt input, we can multiply it by our number at 75 gigahertz, which is 0.632, and we'll get about 2.5 watts at the output, which is above our 2 watt specification, but this is a good place to be because once we do our momentum simulations and combining, we'll have a little bit more losses. So here we can see our layout, which is still in need of optimization. The resistors are much larger than the rest of the design, and that's because we need to plug in the exact parameters for our resistors, and then we'll do momentum simulations for it to factor in any possible coupling, and then we'll be looking forward to next semester.
Okay, so in the previous video we laid down a number of tasks. So far we have done all our research and we have almost done all our design. We have been working on the optimization and simulation of our current design, and then layout design and cost assessment of our prototype. I'll briefly talk about our cost assessment. So the team has a budget of $400, which will be spent on the prototype, and the remaining cost of the overall $1,500 total cost of the prototype will be covered by Cactus Materials. For our next semester, we look forward to work on the thermal management assessment and the prototype implementation. Thanks for watching.